Today we're going to discuss random variables and probability distributions. We will focus on discrete distributions. In terms of the agenda, we will discuss what a random variable and what a probability distribution is. We will then discuss the cumulative distribution function. Finally, we will then talk about two types of discrete distributions, the Poisson distribution and the binomial distribution.
Before we get to the distributions, let's first talk about random variables. A random variable, or RV for short, is any rule that associates a number with each outcome in the set of all possible outcomes in an experiment. It is a variable because different numerical values are possible. It is random because the observed value depends on which possible experimental outcome results. An RV is denoted by uppercase letters such as capital X or capital Y. When we assign probabilities to each outcome, we are setting up the probability distribution. The probability distribution of a random variable says how the total probability is distributed among the various possible values of that random variable. You should note here that the probability for all of the outcomes in the sample space is 1. There are two main types of random variables in probability distributions. These are continuous and discrete. A continuous distribution is one where the possible outcomes consist of an entire interval on the number line. Some examples are the normal and exponential distributions. A discrete distribution is one where the possible outcomes either constitute a finite set or an infinite set with some natural sequencing. Some examples of these are binomial and Poisson. A discrete random variable has a distribution specified by a probability mass function, or PMF. This can be used to get the probability that the random variable x takes on some value little x. These probabilities must be greater than or equal to 0, and the sum of the probabilities for all x must be 1. The cumulative distribution function, or CDF for short, is defined as the probability that the random variable x is less than or equal to some value little x. In the discrete case, this is just the sum of all the probabilities for x going from 0 to x. There are many different types of discrete distributions. For this course, we will focus on the Poisson and binomial distributions. Let's start with the Poisson distribution. The Poisson distribution is a discrete distribution typically used as a model for the number of times an event of some sort occurs during a specified time period or in a particular region of space. There are some examples of this on the slide. You can think about this distribution as being useful for count data.
The PMF for a random variable that has a Poisson distribution is given in the slide. It has parameter lambda, which is typically a rate per unit time or unit area. The parameter must be greater than 0. Also notice that x can take on only integer values going from 0 up to infinity. This shouldn't surprise you since we can't have a negative count. Now to find probabilities, we will just plug in x and lambda to the formula on the slide and solve it. Note that the denominator is x factorial. This is just the product of x and all of the integer values less than x down to 1. Most statistical packages can be used to find these probabilities. Let's look at an example.
Example 1 is a problem in which we have a random variable that represents the number of defects found on a sheet of metal in a manufacturing facility. We know that typically we get 4.5 defects on each sheet. We need to find the probabilities for each situation. Here are the solutions. You should make sure that you can replicate these in all of the results for the examples in the notes. Anytime a problem uses the term typical or expected, that is an indication that this value is the mean. Notice that for the second part of the problem, we need to find less than or equal to 2. So we add up the probabilities that x is equal to all of the values less than and including 2. Also for part 3, we need greater than 2. Now we know that the total probability must be 1, so we can use this to our advantage. Anytime you get a part of the problem that is asking for greater than, we would need to find the probabilities for everything larger than that value. In this case, it would be from 3 to infinity. Now, of course, we will not be able to do this, but we can subtract the opposite probability from 1. So greater than 2 would be 1 minus less than or equal to 2. You should realize that if you are finding probabilities for a large number of values, then you are missing something. The mean and variance for a random variable from the Poisson distribution are both equal and are equal to the rate per unit time or per unit area, which again is the parameter for the distribution. Here is another example. Let's assume that on average there are about 25 imperfections in 100 meters of optical cable. Notice here that we are taking 100 meters of cable as our unit, not 1 meter. Now we would like to know about the probabilities for imperfections in 1 meter of cable. Let's check the solutions. Notice that for 100 meters of cable, we know that the parameter would be 25 imperfections. What we need to find out is what is typical for 1 meter of cable. Based on the change in the units, the rate for 1 meter will be 0.25 imperfections. Note that the 0 factorial is equal to 1. Now we will approach the problem in the same manner as the last one. The other type of discrete distribution is the binomial distribution. This is based on the binomial experiment. There are 4 requirements that must be met in order for an experiment to be considered binomial. The experiment should consist of n fixed trials a priori. The outcome from each trial is dichotomous, denoted by a success or a failure. Each trial is independent. The probability of a success is constant from one trial to the next, and denoted by the parameter pi. There are some things to note here. Since the trials are independent, this type of sampling is considered sampling without replacement. The number of trials should be set before the experiment begins. This is done so that the experiment is not cut short when the outcome is not favorable, or is extended when it is. Also, consider the term success. This is set initially and is only considered favorable from an experimental standpoint. As an example, in manufacturing, a defect is actually considered a success when assessing the probabilities, or percent defective. Let's look at the binomial distribution. The RVX is defined as the number of successes in n trials. The parameters for this distribution are n and pi. The PMF for this distribution is given on the slide. The first piece is the number of ways that x objects can be chosen from n possible objects. The second piece is the probability of a success raised to the power the number of successes. The third piece is the probability of a failure raised to the power the number of failures. Notice that x can take on integer values from 0 to n. Let's look at an example. A large chain retailer purchases a certain kind of electronic device from a manufacturer. The manufacturer claims that the defective rate of the device is 3%. The retailer chooses 20 items from a shipment to inspect. This is binomial since we have 20 fixed trials, and each trial can end with one of 2 outcomes, and the probability of a success is fixed at 3%. The solutions are on the next slide. For this problem, we will just use the binomial PMF with n equal to 20 and pi equal to 0.03. Notice that for greater than or equal to, we use 1 minus the less than. Now, a problem that we can come across is that even when n is small, the computations to find the binomial probabilities can be tedious. For example, what if n were equal to 20 and we would like to know the probability that x is less than 12? We don't want to do probabilities for 11 through 0 or 12 through 20. To meet this end, binomial tables have been created based on the CDF for a set of given n and pi. Since there are many different combinations of n and pi, these tables have limitations. Most statistical packages have built-in probability distribution calculators. Minitab is one of these. For the binomial distribution, the mean is the expected number of successes. This is calculated by n times pi. The variance of the random variable is the mean times the probability of a failure, or n times pi times 1 minus pi. Let's do another example. This example is one where 20% of all copies of a textbook fail some binding test. Let X denote the number among the 15 randomly selected copies that fail the test. This is a binomial experiment since we have 15 fixed trials. The outcome is dichotomous and the probability of a success is fixed. The solutions are on the next slide. Notice that for part 1 we would need to sum all of the probabilities from 0 to 8. In this case you would want to use the tables or a package. For part 3, notice that since it is greater than or equal to, we change it to 1 minus the less than. In order to use the CDF, we should change it from less than 8 to less than or equal to 7. Probably the most critical ability in this situation is to be able to decide which distribution should be used. If you have count data based on some unit, whether it be time or space, then we use Poisson. If we have a dichotomous variable, then we will use binomial.